Okay, guys. The next topic here in electrodynamics is the concept of drift speed of the charge carriers. When you say charge carriers, they say in general charge carriers, but we know that actually the charge carriers are the electrons, right? So I put this drawing here. So, but what is exactly is happening? When you are in high school, we learned I think most people learn in high school that you have like the electrons like just flowing through the wires, right? At a or velocity close to the speed of light, but that's not actually true. What happens is quite different, right? When the electrons inside like a conductor, they move quite randomly in many directions all the time. So this guy here makes us a very good job, because he trying to simulate in 2D what is going on. Actually, for every atom that you have inside, like composing the wire, you have about like an average like one free electron that actually is moving randomly, and the velocity for this movement is actually, since it's random, right, it doesn't move like in one direction. So there's many random directions. This is way lower than the speed of light. So you have something like this, right? You have this is the lattice inside the material. This you have the atoms, and then you have the electrons, the free electrons, like moving randomly inside the material. And as soon as you the guy doesn't do have. Let's see if we can find microscopic view. Microscopic view. No, the last show. Yes. And when you have when you have this wire and the subjected of electric field, then doesn't matter if you put like electric, you have an electric field here. And so these electrons, they start to move. They still move randomly, but they slowly, that's the main point here, they keep moving randomly like you saw in that simulation there, but they start moving slowly in one direction, preferentially direction. As a, if you have like the positive, like positive potential here and negative here, that means that you have the electrons moving from one higher potential to a lower potential, right? In this sense, these electrons are going to slowly drift in that direction, right? From our left to the right. And this is what we call the net velocity of all these electrons like moving, is what we call drift velocity. Yeah, I hope you know that. So let's try to derive one expression for this drift velocity. Let's consider here a wire, right, with this, and I'm considering one particular element of volume inside this wire. Since the wire can be approached as cylindrical, right, guys, we know that the volume of a cylinder, all you have to do is multiply this area, right, that I have here by the size of or the height of this cylinder. And at the same time, I know that this cylinder here, this element of volume here, is going to be defined by this Vd, that is actually, Vd is the drift velocity. So if I plug in here, what you have is actually one expression for this volume, right? This volume here as a function of the area and the drift velocity and this time here. Okay, guys, so all the charges in this volume here, they move out in this infinitesimal time dt here. And with these charges, all these charges here I represent graphically here, they all have a drift velocity Vd. And we define one very important definition here. The number of free charges here we call n. This is going to be the number of charges divided by the volume. And the volume, we just have one, you just found one expression here, right? You can actually start making this expression a little bit more robust. So, and well, some things that we have to talk about this free charge, the number of free charge for unit volume, right? First of all, this value depends on the material, clearly. And the shaded segment has a volume that we know here, so the number of free charges in the volume is, you just have to multiply by this, right? If you wanna, all you have to do here, if you wanna know the number of charges like running through this wire here, all you have to do is multiply this number here the density of free charges. We have to multiply this by the number of charges. Sorry, I have to multiply by the volume. So it's going to give you since we found one expression here for this volume, you can actually write this as N A the drift times the drift velocity and times dt. Right, guys? Wow. But you know already, right? Since we know that we just defined that the electric current is the temporal rate of charge, right? This is the, we can actually, if you divide everything here by dt, what you have here is actually one expression for this drift velocity in terms of the electric current and this density of free charges. And sorry, to keep this in mind, and you can write that actually this as an E A drift velocity and this is what interested us, right? This is the important result here. We can use this to solve problems. And E, don't forget, E is the charge of the elementary charge of the electron that we mentioned like in first class. Where is it? Let's go back to our first class right here. So this is the elementary charge. Go back. No need to put this back. And from here you can actually define, you can put here that the drift velocity is going to be I, the electric current divided by N, the density of three charges, times the the elementary charge times the cross-sectional area of the conductor. So this is important result for us. And this VD is, we call drift speed, N is the free charge density, A is the cross-sectional area of the wire, guys, and I is the electric current, and this one, as I mentioned before, this is the elementary charge of the electron. Let's go here. So in this case here, this is all I have to do here, and I wanna solve one problem for you guys to see. Oh, do I have a problem for this? No, not yet. Okay, so what I wanna talk, but this is already known to everybody, right? The resistance of a conductor. We have two main characteristics that are interested when you talk about like currents in conductors. The first one is the resistance, and the other one is the resistivity. The resistance is what I'm showing you here, right? Is just this ratio. This is also known as the first Ohm's law, and this is a property of the object. So every single object has a resistance. And what I'm going to talk next, that we call resistivity. The resistivity is a property of the substance, of the element, and is not related actually with the object itself. So this is object, and as you remember, we represent the resistance as has this kind of symbol. This depend on the country actually. Some countries use this symbol on the left, and some countries use this symbol on the right. I don't remember each one uses which. No idea, guys. If you know, yeah, let me know. And the SE units for the resistance. This is a review, that's why I'm going very fast. Is the on. So this is volt per ampere. This on, and let's see one small simulation here to what represents that. Dun, dun, dun. Let's see. Okay. So this relationship, this is known as the Ohm's law. If you increase, okay, the resistance is, as I told you, is a property of the object. So that means that the V and I are proportional, right? So this is what we can see here. Funny, even with sound. So if I increase the voltage, I'm going to increase the current as well. See, this ratio should be constant, and this ratio is known as resistance. Okay, let's go ahead. But because now we are interested in describing like current, not something connected with the object itself, but with the material, we do not focus anymore on the voltage, and we are trying to use the electric potential actually. The electric field. Sorry, not electric potential. We are trying to use electric field at any given point in a resistive material to represent that, and then we are going to use also the concept of the current density, and then we define the other property of the material, right? We learn a little bit different way this in high school. We learn what is called this Ohm's second law, right? that the resistance of the material is directly proportional. If you consider like a cylinder, right, of with a given length and a given area, length, oh my god, my theme, like this, right? So you can actually calculate. Remember, this is a property of the material itself and not the object, right? But here you have a different way of defining this, and you are going to see why later. We have then that the resistivity of the material, all you have to do is just divide, is just the ratio between the electric field in a given point by the resistivity, right? Sorry, of electric current density in that point. And this is what you are going to use, because this is in the doesn't depend on the object itself and only on the material, so doesn't matter the shape or everything else, you can actually calculate. And also sometimes often we're talking about the conductivity, and the conductivity is very easy. It's just the reciprocal of the resistivity. That means it's 1 over, and I don't know why this is supposed to be sigma here. What is that? Insert equation. Where's sigma? Sigma. Okay, sigma. Okay, the resistivity, guys. If we define the resistivity as the electric field divided the current density, the electric field is going to be voltmeters, the unit, and the current density is the ampere per square meters. If we solve this, we are going to find volt over ampere times meter, and this volt times amperes is on. Hold on. So the unit for the resistivity is on meter, and of course since the units for resistivity is on meter, the units, the SI unit for the conductivity is going to be the reciprocal, right? Is ohm meters to the -1, or sometimes people say mHOs per meter. They just invert this, and so it's really up to you how you're going to call. Most of physicists, we concentrate actually in saying that this is ohm meters to the -1. Also, guys, since we know this definition here for the resistivity, sometimes you are going to see that some people represent instead of representing this relationship here in terms of the resistivity, some people represent this relationship here between the electric field resistivity and current density. They just plug in the conductivity here, 1 over sigma, and then we can easily find this expression right here. Okay, let's go forward. We don't have much time. Let's see what I have to do now. Give me a second here, guys. Just organizing, just separating my notes a little bit. Okay, done. Oh, okay, with this also is very important to show you guys. Sorry, I forgot to show you something. I would like to show you some typical values for resistivity. As you can see here, for this, you have very low values of resistivity for metals, right? for the most common metals. For example, you know that most wires are made of copper, and if you have like some high precision circuits, in general we use silver and gold. As you can see, the resistivity is relatively low for this kind of materials, right? That means that the conductivity is very high for this kind of materials. And on the other hand, you can see that actually you have some materials with very high resistivity. That means that they have very low conductivity. They are not good conductors. That's what I mean with that. These are some typical values I found only for those guys. Maybe I should put some. I'm going to include later, man. I'm going to include these values for some superconductors or semiconductors as well, so you can have an idea. But I think in the textbook you can find as well. Let's see, just for fun, if you can find. I don't know where I put. So let's move. That's easy. So, and I'm going to solve a problem, guys. How many people have in class today? Yes. 1 second, I'm going to grab the attendance. Dun, dun, dun.